Today I would like to solve a few questions. Let's start first with parallel plate capacitor. The question is the following. A parallel plate capacitor is made from two square plates, side length 12 centimeter, which are 4.5 millimeter apart. 2/3 of this gap contains air, but the bottom third is filled with dielectric material of a dielectric constant 3.4. The voltage drop across the two plates is 18 volt. A. What is the capacitance of this combination? B. How much energy is stored in the capacitor? C. If we remove the dielectric material but change nothing else, how much energy will it be stored in the capacitor? So let's start with the first part. Part A. We have a square electrode. Both electrodes are square shape. The distance D equals to 4.5 millimeter. The edge is 12 centimeter. This is 12 centimeter. One third is filled with dielectric. So this is D1, 1/3 of D. Then we have this as 2/3 of D. We have the dielectric constant for this material. K is a 3.4. However, K for air is 1. This is the structure that we would like to find the equivalent capacitance for. So just by looking at this capacitor, finding that one electrode is connected to the dielectric here from this side, the other electrode is connected to the air. This tells me that those two capacitors, if I'm to call the one with the air as C1, then the capacitor C1 is connected in series with the capacitor C2, and both electrodes is connected to the 18 volt source. So in this case, now if we want to calculate the capacitance C1, we can use the ideal equation for calculating the capacitance, which is C equals to epsilon A over D, where D is the gap between the two electrodes and A is the overlap area, and epsilon is the material permittivity. So for C1, we know that C1 as for the air case, so C1 equals to epsilon naught, because the dielectric constant is 1 for air, times A divided by the distance d1 here is 2/3 of d. So if this is in general, then here for the C1 case, my distance here is d, and the gap for the air-filled capacitor is 2/3 of the total distance. So C1 equals to 8.854 10 to the power minus 12 times 12 centimeter squared divided by 2/3 of 4.5 millimeter. C equals to 42.5 picofarad. Now for C2 we have K2 epsilon naught A divided by D2, and in this case we know that this is 3.4 times 8.854 10 to the power minus 12 times 12 centimeter squared divided by 1/3 of 4.5 10 to the power minus 3. And in this case C2 equals to 289 picofarad. So C1 is 42.5, C2 is 289, and as we said, C1 and C2 are in series, so in this case we can say that C equivalent equals to C1 times C2 divided by C1 plus C2, and C equivalent as 42.5 10 to the power minus 12 times 289 is 12 divided by 42.5 is 12 plus 289 12. And C equivalent as 37.1 picofarad. So this is the C equivalent for this structure. So this is A, now for B we need to calculate the energy stored in this capacitor. We know that the energy for the capacitor equals to half CV squared, which is E equals to half times 37.1 minus 12 times 18 squared. Energy as 6.01 times 10 to the power minus 9 joules. C is what happens when I replace this dielectric with air. In this case, I have a new capacitance, and this new capacitance will have a dielectric constant of 1 epsilon naught. A is the same, however now the whole distance would be the distance, the whole gap now will be for the air-filled capacitor. So in this case, C nu is 8.854 10 to the power minus 12 times 12 centimeter squared divided by 4.5 10 to the power minus 3, and C nu in this case would be 28.3 picofarad. It is expected to be smaller than the C equivalent because the dielectric constant now has been changed to air. Okay, so the last part is the new stored energy. So E nu is half C nu V squared, did not change, so we have E is half times 28.3 10 to the power minus 12 times 18 squared. Is 4.58 10 to the power minus 9 joules. Okay, now let's move to the second question. In the second question, we have a square shape of 220 turn coil with a side length of 75 centimeter and is located in a region with a steady and uniform magnetic field of magnitude 1.15 Tesla directed into the page. The area vector A of the loop is initially parallel to the magnetic field, which means that the unit vector is in the same direction. The coil is then rotated about its central axis, as shown here in the figure, at an angular frequency of 3.2 radians per second. What is the induced electromotive force in the square loop 1 second after it begins rotating? So we have this is square, it can rotate around this axis, the magnetic field is entering into the page. Uniform magnetic field. So we need to calculate the induced electromotive force. Okay, if I am to look from this side, I will be seeing that magnetic field are in this direction, also the loop. I will only see one side of the loop, so let me draw the loop. So the loop is going to look to be as this, or the coil. While its unit vector is in this direction. So this is B. Okay. This is the A vector. Now if this loop is going to rotate, then I will draw the new location in dashed line. The angle between the magnetic field and the area vector would be this theta, based on the rotation that I have here. This rotation is going to look like this. So let's put the equation for the electromotive force. So I have electromotive force equals to minus N d phi over dt we know that the phi is the magnetic flux minus N, so this is going to be d over dt for B dot A, which gives electromotive force equals to minus N d over dt B A cosine theta from the dot product of two vectors. If A is as an area is constant and B also is uniform, the only variable that is changing is theta. So in this case I would say that electromotive force equals to minus N B A d over dt cosine theta, which is minus N B A minus sine theta d theta over dt, and this gives electromotive force to be NBA sine theta, and then d theta over dt can be replaced by the angular frequency omega, we also know that theta is omega times t, which is, in this case, I have electromotive force as NBA sine omega t times omega. Now if we substitute, N was given to me as 220, the magnetic field was 1.15, the area was a square 75 centimeter times sine omega t. Omega is 3.2 radians per second. We are evaluating it at 1 second times 3.2 and this gives electromotive force to be minus 26.6 volts. Notice that this is omega radian, so the theta here will be in radians, and induced electromotive force would be minus 26.6 volts. The third question is also a capacitor of 6 microfarad that is initially uncharged, and the switch was open. Immediately after closing the switch, what is the current through the 10 ohm resistor? This is part A. Part B, after the switch has been closed for a long time, what will the current through the 10 ohm resistor be? Part C, after the switch has been closed for a long time, how much a charge will there be on the capacitor? I have ohm, 45 ohm, 25 ohm, then capacitor, switch, 15 volt, and this is 6 microfarad. So right after the switch is closed, basically means if we assume that the switch is going to close at t equals 0, so I'm interested to calculate here the current through the 10 ohm resistor right after the switch is closed, which means at the moment that we call t equals to 0 plus. So if I am to have the switching happening at t equals 0, then the moment right before the switching is happening, I'm calling it 0 minus, and right after the switching is happening, I'm calling it 0 plus. So in this case, I will be relying on the continuous behavior of the voltage across the capacitor, which means that the voltage at 0 minus should equal to the voltage across the capacitor at 0 plus. So if the capacitor was fully discharged before the switching, this means the voltage across the capacitor was before the switching was 0, and it will continue to be 0 right at the moment after the switch is closed. In this case, if there were no charges stored in the capacitor, I can treat the capacitor, as long as it has 0 voltage, I can treat the capacitor as a piece of wire. So I can remove now this capacitor. So let me delete the switch here and delete this capacitor here, and then call this at t equals to 0 plus, and then replace the capacitor with a piece of wire, and of course now the switch is closed. So this is the circuit for the 0 plus moment. Now I will need to calculate the current. Which is this current. Let me call this one I1. So in this case, I have 45 and 25 ohms are connected in parallel. So I can say that I1 equals to 15 volt divided by R equivalent, and this R equivalent is indeed the 10 ohm plus the 45 that is in parallel with 25, so 45 times 25 divided by 45 plus 25, and this is going to give me R equivalent to be 26.1 ohm and I1 to be 0.57 ampere. Now the next part is we need the voltage drop here. After the switch has been closed for a long time, what is the current through the 10 ohm resistor? So in this case, we're looking at the t equals to infinity case. So for the t equals to infinity, which is long time, I will redraw the circuit for the T infinity, and in this case the capacitor would have reached the steady state, would have been charged either to the maximum of the voltage or completely discharged, based on how this capacitor is connected in the circuit. So let's look at our circuit here. If I am to redraw now the circuit and replacing the capacitor with an open circuit, because right at the t equals to infinity there will be no time varying current. In this case the capacitor would have reached to its maximum, or whatever charge it is applied across, and in this case I can replace the capacitor at t equals infinity with an open circuit. So let me redraw the circuit now. Replacing the capacitor with an open circuit. Now this is VC at the moment of infinity, 45 ohm, 25, 10 ohm, 15 volts. Now we need I2. So as I said, in this case the capacitor now will reach its steady state, and the capacitor now can be replaced by an open circuit. So if I want to calculate the current through the 10 ohm, as I said, since this one is an open circuit, there is no current. The current going in here is 0. That's an open circuit, which means I2 will only go through the 10 ohm and the 45 ohm resistor, and in this case I2 becomes 15 divided by 10 plus 45, and I2 here becomes 0.27 ampere. After the switch has been closed for a long time, how much a charge will there be on the capacitor? So we need to calculate the charge that will be stored in this capacitor after the switch has been closed for a long time. In this case we will need first to calculate this voltage that is across this capacitor, and as I said here, because the circuit here is broken, there's no current going into this branch, the voltage across the capacitor will be the same as the voltage across the 45 ohm. Why? Because there's no current going into the 25 ohm. In this case the voltage across the VC equals the voltage across the 45 ohm, and in this case if I have calculated I2, then VC would be 45 times I2 0.27, and in this case VC would be equal to 12.27 volts. Now if I found the voltage, then I can find the charge, since I have the capacitance. So in this case I know that Q equals to CV, I know C, I know V, and then I can calculate Q. So this is C, and Q equals to 6 microfarad times 12.27. Q equals to 73.64 10 to the power minus 6 coulombs. The last question is circular wire coil of radius 10 centimeter that has an 880 turns and is constructed from number 30 gauge copper wire. The diameter for that standard is 0.256 millimeter. So this is the diameter of the wire. The loop is placed in a region of uniform magnetic field and is fixed at an angle of 45 degrees with respect to the magnetic field as shown in the diagram. What is the resistance of the wire loop? A. And then B. Calculate the magnitude of the induced current in the loop at time equals to 2.5 seconds if the uniform magnetic field has a time dependence given by 1.5 minus 0.05 t squared. First of all, let's calculate the resistance of this coil. We know that the radius for the coil, so if I am to draw the coil here, so this is the radius of one loop, and this is the diameter d of the wire. We have 880 turns, and we need at the beginning to calculate resistance for this coil. So we know that the resistance equals to the resistivity times the length divided by the cross section. We also know that this length is proportional to the number of turns. So in this case the length is 2 pi r times n. So it is not on, this is for one loop, however I have n loops, so the length would be this one loop multiplied by the number of loops. I also know that the cross section A is pi d divided by 2 squared. The resistivity for the copper is given as 1.72 10 to the power minus 8 ohm meter. So now if I put everything together, then the diameter is given to me, the radius is given to me, the number of turns is given to me. I have the resistivity of the copper, then I can find the resistance as 1.72 10 to the power minus 8 times 2 pi times 10 to the power minus 2 times 880 divided by pi 0.256 squared. And in this case, the resistance of this coil would be 185 ohm. Part B is calculating the induced current at a tilted angle. So we know that the electromotive force equals to minus N dphi over dt, which is minus N d over dt for the magnetic flux B dot A this gives equals to minus N d over dt B A cosine theta from the definition of the dot product, then equals to minus N A cosine theta goes outside dB over dt, which is a time dependent, where dB over dt will be minus 0.05 times 2t. Now, if we substitute dB over dt with its equivalence, then this is minus N A cosine theta times minus 0.1 t, and if I am to substitute, then electromotive force epsilon equals to minus will cancel, so I have here 0.1 times N times A times cosine theta times T .1 times 880 times 10 centimeters squared times cosine 45 times 2.5 electromotive force will be 4.88 volts. So the induced current I induced equals to 4.88 divided by 185 I induced equals to 26.4 milliampere.